Hi, everyone. Safety critical is everywhere around us, even though we might not notice it. Because we have software is permeating all aspects of our lives. And we are also noticing that some places, if software goes wrong, people might actually get hurt. Thinking like cars, the software that controls the brakes. Thinking like airplanes, medical devices that let people with certain conditions continue to live. And because if you have your mobile application that delivers food, for example, if the application stops working, it's not such a big problem. But if instead you get to a car and the brakes stop working, that is way more serious. And that's what safety critical is. Safety criticals are, or functional safety, are all of the systems that where a failure could harm a human life, where something going wrong could be catastrophic. And it's actually one of the few parts of our sector that are regulated. It's programming is quite weird because anyone can do it. While if we compare to any other engineering area, there are state exams, there are certifications that you need to have. And safety critical software is the only place in software where that is present. And one crucial thing about safety critical is that it requires qualified tools. You cannot just use any off-the-shelf compiler. And one of those tools is a qualified compiler. And that's what we built at Ferrosystems. We created Ferrocene, which is a qualified compiler for Rust. And in this talk, I want to go a bit on what does it take to qualify a compiler? What does it mean for something to be qualified or certified for safety critical? And what is the process? Because I think that it's something that everyone has a vague intuition of yeah, it should be safe, it should not have bugs, but what does it take in practice? So hi, I'm Pietro. I am the technical lead of Ferrosystems for Ferrocene. And I'm also a bit less nowadays, but I'm also involved in the Rust project. So I'm part of infrastructure, release, and security teams. And also previously, I was on the Rust core team, and I led the infrastructure team before JD, who spoke earlier at the conference. So let's start. What is safety critical? I kind of mentioned it already before, but safety critical is any system where any malfunction could actually harm a human life. And there are a lot of areas that are safety critical. And crucially, each of those areas have some regulations for what you have to do to get your software qualified and certified for safety critical. And all of these are kind of the same in the sense that the general principles of all of these standards for the various areas in the industry do kind of push in the same direction, but each of them have slight differences on how they call stuff, on some requirements that are specific to that environment. Each of the standards, unfortunately, most of them are paid. You cannot actually go and buy and read them without buying them. And they are they're not actually that boring. Because a thing that safety standards do is that they don't prescribe what you have to do. You're never going to find in a safety standard for safety critical, you actually need to use this technology and this piece of software or do this in this specific process. What they do is they tell you what the goal that you should achieve. What is why and what you need to do something. For example, an example I always like to make is no safety standard actually tells you you have to use Git or you have to use a version control. What they may tell you is you have to have processes in place so that you can track changes and who made those changes. And if your approach is to have your developers fax the difference to a notary to be notarized every single time, that totally works for safety critical. You probably don't want to do it, and you probably just want to use Git. But you just have to figure out a procedure that works for you and works for your project, and document it and follow it. Another really important thing to think about is the difference between qualification and certification. Because those are terms that I often see used interchangeably, but they're actually very different because certification is for what actually goes into the safety critical system. So for example, what goes into the car, what goes into the plane. While qualified tools are used to produce the certified software. And it's a bit weird because qualified tools are never mentioned in, for example, the automotive standards. And you can build your safety critical software without using any qualified tool. Because what actually the standard mandates, and that gives back to the thing I mentioned before of the standard never say the exact procedures you need to follow. The standards want you to review what goes into the safety critical system. So in this example, we have some schema, for example, for a remote procedural call protocol that goes for a generator to output source code that then goes into the compiler that gives you the executable or the library. And the standard says that you need to review what goes into the system. So if you take that literally, it means that you have to manually review the executable that goes into the car, which means manually reviewing the assembly generated by the compiler. And nobody wants to do that because we are our time and not wanting to spend weeks just reviewing a single module. What qualified tools do is they move the bar where review has to be done. So for example, if you take a qualified compiler, the review is moved to the source code. So you have to review that the source code does what you want, do all of the verification that is required for certification and all of that. But since you use a qualified compiler, the output of the compiler is assumed to be good. It's assumed to be that the compiler correctly translates the source code into the executable you want. And it doesn't miscompile something. And if you wanted to go also further, you could qualify the code generator you use, so that you don't even have to review the source code that is generated. If you have both tools qualified and they speak the same language, then you just need to review the high-level schema. And which level to qualify and how many qualified tools you want to use is often a business decision. Because qualification is quite expensive. It takes a lot of resources to do. And it's quite expensive. And so it almost always makes sense to use a qualified compiler because nobody wants to review assembly. But if the output of the code generator is fairly readable, it might not make sense to go through the trouble of qualifying it. And so you might just want to say, the schema can be whatever, what we review is the source code. But what does it actually mean for a tool to be qualified? And for context, in the rest of the talk, I'm going to cover only qualification, not certification. A tool being qualified doesn't mean that it doesn't have bugs. Because you cannot write a program that doesn't have any bugs. If someone can figure out how to do it, let's revolutionize the industry. It's not possible. What it means is that you have done your due diligence to prevent bugs from happening. You must have done enough and done the best you can to ensure that it's rare that bugs sneak in. And also, the other important part is quality management. So what do you do if a bug sneaks in? What are our processes for developing to ensuring that there are no bugs in the resulting software? And quality management is a fancy word for saying that you must have the processes in place in your company to guarantee that quality. And you must follow them. And that brings me to Ferrocene. Ferrocene, which is the thing Ferrosystems has been working on for years now, and is the first qualified Rust compiler. And it's currently qualified for automotive and industrial safety to the highest level of assurance, which means that now you actually have a qualified compiler to be able to write in Rust the software that powers the brakes of your car, the airbags of your car, those systems that absolutely have to work. Thanks to Ferrocene, Rust is now a valid language to use in those contexts. And a thing I really like about Ferrocene is that it's fully open source. The safety critical industry, especially for toolchains, is very rooted into the old proprietary, extremely expensive tools. But for Ferrocene, we wanted to kind of bring some of Rust's magic into safety critical, not just the language, but also the ecosystem, the way things are developed. And having everything open source includes having all of the documentation that we are producing be open source. All the documentations that we are then going to send to the assessors to verify. And as far as I'm aware, this is actually a first in the industry. You might have compilers that are open source, mostly because they're based on GCC and thus have to provide you the source code, but nobody before us actually published the qualification documents. And so that's kind of what I want to do in the talk. Let's go through them. Let's actually see what does it take to qualify a compiler. All of the steps that we have to take to go from the upstream compiler that you all love and use to something that is used in the automotive industry, for example. And a disclaimer, there is very little boilerplate. And this was actually something that surprised me when I joined Ferrocene, because I didn't have any previous experience with safety critical. I was working on the Rust project on the infrastructure, making sure that you can download Rust. And, but there's actually very little boilerplate. There are very few pieces of documentation that are just present for the sake of it, for the sake of documentation. And most of that has an actual practical use. And so we can go into the first step, which is the evaluation. So doing an analysis on the software you're about to qualify and figure out exactly how much work do you need to do to qualify? What are the steps you need to take? Because I will see later, it's vastly different depending on the software and the impact the software can be. There are very different amount of steps to take. And again, as I said before, the standards don't prescribe that you need to have an evaluation and how you structure it. The way we chose to structure it is to split it into two documents. We have the evaluation plan, where we describe all of the processes that we take. So how are we going to do this evaluation? And then we have the evaluation report, which contains the outcome. So what did we find during the evaluation, and what is the result? What steps do we need to take next? And the first step of the evaluation for us was defining the use cases. How can you use Ferrocene? And this is not a pointless effort. It's going to be useful later. And for Ferrocene, we actually found 4 use cases. Because it's a compiler. You, of course, need to install it. And then you use it to build a project, a library, a program, an executable. And this effort is useful for the next phase, which is, how can the software fail? What are the ways that the tool can introduce a bug, can result in the code that it generates not being what you expected? And having a list of use cases is actually fairly useful for that, because you might not think of considering installing Ferrocene as a use case, but having that as a use case and having to figure out the failures of that, for example, allows you to figure out, hey, a failure possibility could be if you mix files from different Ferrocene releases, what would happen then? And for us, the way we do this analysis is through what we call the hazard and operability study, or HAZOP, as I'm going to call it later. And the HAZOP is basically sitting down and trying to figure out all of the possible ways the software could fail. And writing them down, we chose to just write them down in Google Sheets. And so we had a huge table of all of the possible ways it could fail, and some of them, like these ones highlighted in green at the top, were things that we thought it was a possible failure, but in practice it wasn't. Like, there was no way for that failure case to happen. And there are instead some possible failure cases that are indeed possible, and we need to figure out how to prevent them, how to make sure that they don't happen when users use our safety-critical compiler. Which brings me to the next step, which is how can those failures be addressed? And again, this is all analysis. This is just ahead of time trying to figure out what work we want to do. And there are actually two ways to figure out the possible ways software to address those failures. One of them is through testing, is to write tests, reuse tests that exercise that part of the compiler and that verify that failure is not likely to happen. And of course, this doesn't guarantee that it's never going to happen, because in software, the test suite there might be a corner case missed by the test suite. There might be a bug we didn't anticipate. But there is also another option, which is to just tell the user they need to manually do something, to constrain through documentation how the user can use the tool. And I'm going to go a bit more into how that looks later down in the talk. But having those two options mean we have two ways to prevent the failures. And for each of the failures we identified in the HAZOP, we then had to figure out, for each one, how is that preventable? And so now we did all of these analyses. We knew exactly how we wanted our users to use the software, how it could fail, and how we can prevent it. And we needed now just the last step of the evaluation, because it's figuring out how much work do we actually need to do for the qualification. And I'll actually use the automotive terminology for the rest of the presentation, because a fairly annoying thing is that every single standard calls things differently, in the sense that one standard might call safety level 1 to 4, and another standard might call the same 4 to 1, or A to C. Like, it's extremely inconsistent. I'll just pick the automotive terminology. First, we need to figure out where we expect our software to live. Because the software that powers the air conditioning of the car has vastly different safety requirements than the software that allows to trigger airbags. Like, if the air conditioning doesn't work, it's going to be an unpleasant car trip. If the airbags doesn't work, let's not talk about that. And depending on this level, which is in automotive is called ASIL, so for automotive safety integrity level, it can go from A to D. And usually, users of the compiler just pick the one that their product will go towards. For Ferrocene, we were kind of forced to go for ASIL D, so the highest level of assurance, because for us, it meant that the compiler could be used anywhere. And then we need to figure out, what is the tool impact? Can the tool introduce errors? Can those errors be missed? And then it's a simple answer. No, like, there is no way that the tool could cause a failure or an error in the resulting code. For example, a linter is probably not going to cause a failure. Or yes, like a compiler could introduce a miscompilation. And the last thing we need to determine is how likely it is that those errors can be detected. How likely it is that a user could detect something is wrong. And for a compiler, it's really hard, because if a compiler produces the wrong machine code, unless your test catches it, good luck figuring that out. And then you just plug everything into a matrix. And you see that if the tool integrity is 1, so that the tool cannot impact the safety of the overall system, then it's always the highest confidence level. And so that will mean we have to do less work to qualify. While if it's TI2, so it can impact the safety of the system, then we might have to do more work depending on how likely it is that an error could be detected. For example, RASC, the compiler, is TCL-free, because it's possible for the compiler to affect the safety of the overall system, and it's really hard to detect miscompilations. But it's not always TCL-free. For example, let's take Rust format. And to be clear, this is provisional. We haven't, while for us it's approved by the assessors, this is our current in-progress analysis. But Rust format can definitely impact the safety of the system, because if when you run Rust format, it outputs some code that doesn't have the same meaning as before, it will impact the overall system. But it's really easy to detect if Rust format did something wrong. You just have to review the code it generates. You just use Rust format in a repository that has version control, and you check the diff of it. And so that is TCL1. And as I said, this determines the scope of work. So in automotive, TCL1 doesn't require qualification. And that's why it's important to do the evaluation, because if possible, you don't want to spend a year or two going through the qualification process if you can avoid it. And with this, for example, for Ferrocene, we identified that Ferrocene is TCL-free. It has the highest level of risk, and thus we need to do qualification. And now I need to drink something if you want to listen for the rest of the talk. Let's go next. Let's start with the actual qualification. And the first thing is writing requirements and testing them. So in short, figuring out what is our software actually supposed to do, how it's supposed to behave, and ensuring that we have enough test coverage that we are verifying all of these use cases. And for a compiler, it's actually both simple and hard, because realistically, apart from a few requirements on the command line interface, the bulk of the requirements of a compiler are the language specification. What is the compiler supposed to do with the input you give? What programs are accepted and how they should be converted? And it's easy because you just have the language specification, but it was hard because there was no unified and complete Rust specification. There were efforts like the Rust reference, but they were not complete. And so what we did is we just created one. We sat down, and we spent around 6 months, I think, with a few full-time people working on it. And we went through everything, and we wrote the Ferrocene language specification. To be clear, it's not the official specification of the Rust programming language, because that's something that the Rust project is actually working on right now. We have Mara at the conference, who is on the team working on the specification. And this is not something official. This is just our requirements document that we use for our purposes. And we decided to publish it in open source if you find it useful for your own purposes. And as a quick aside, because this is just a fun anecdote, the whole language specification was actually written in Google Docs. So we had a very weird and very long Google Docs documents where we basically created a dialect where, for example, different fonts meant different things, words highlighted in yellow were going to be turned into links. We had one bookmark for every single paragraph, except for one time when a script went wrong and created 100,000 bookmarks in a document, and the document was really slow to use. But why did we do that way? Why didn't we just use GitHub and put markdown files or structured text files in a Git repository? Well, because you really have to use the best tool for the job. And for us, working on a large technical document, Google Docs was actually the best choice, because it allowed us to be able to quickly comment and suggest fixes all across the document. I think I have never used a system that provides real-time comments and suggestions as good as Google Docs. And so this is just a small aside of using Git and having everything done through GitHub is not always the best tool for the job. And make sure that you consider the requirements you have for what your tooling wants to do before committing to a choice. But now we had, 6 months later, we had a full language specification. And now we needed to ensure that we actually tested it, ensuring that every single section of the specification had some tests that proved it was correct. The way we did it is that we had every single section of the FLS had random IDs. They were random because that way they were static even though the content might change, so we didn't have to redo the test annotations. And then we went through the entire Rust upstream test suite, and we added comments linking the annotations. And here I actually want to give a shout out to the Rust project as a whole, because we actually didn't have to write any test, practically. Like, we had a few of them, but like, the Rust test suite was good enough that it was able to cover all of the language and all of the language specification. And so at that point, we had a full list of requirements, a whole test suite with annotations, and we needed to merge it together through the traceability matrix. And the traceability matrix is a document that shows that merges the two information together, and for every single section, ensures that you have the good test coverage. So this is the actual traceability matrix for Ferrocene. And it's a very large and heavy page, because in addition to the summary, for each individual test, for each individual section, it links all of the tests in the Rust test suite that cover that part of the language. And this was a very boring manual effort to go through all of the tests and categorize them. And this is, in the end, what we give to our assessors, how we can prove that we have the confidence that the bugs are not likely to be there. Because, let's be frank, Ferrocene already has bugs. Ferrocene are going to have bugs. And it's impossible to prevent all of them. But this showed that we did our best, we did our due diligence to ensure those bugs are not present. And again, nothing in the standards say you have to do a traceability matrix. This was our process. If your company and you want to qualify another tool works best with a different process, just document it for the assessors. And then we dive into the last part of what does it take to qualify a compiler, which is the quality management. And quality management is described in our qualification plan. And it describes all of the processes we follow. And crucially, quality management is not something you can sprinkle on the project at the end. It's not a layer of paint to add to it. It's the whole development cycle. It starts from what do we want, planning what do we want to do, to implementing it, to building it, testing, shipping it to customers, and how do you support customers afterwards. It's all of the documentation, it documents all of the processes, and actually having them written down is good. And like, it doesn't have to be enterprisey, very paperwork-heavy process. You define the processes. The standard don't mandate anything. I'm repeating that a lot in the talk. And for us, we said, let's get inspired by Rust. Let's not just use the Rust compiler, but also use their development practices. And there are two reasons why we did that. One is that Rust practices are actually very good. Like, Rust is one of the open source compilers with the best quality management all around. And that is proven by the fact that Rust can ship new releases every 6 weeks with very little regressions. And also, a lot of employees of Ferro Systems are former members of the Rust project, so this was the process that was familiar for us. This was the process that worked for us. And for the development, the easy answer is that we need to have mandatory code reviews for everything, and we use merge queues to test changes. Merge queues in the Rust ecosystem are also called BORs, which is the name of the bot we use. And this comes from Graydon Hoare, the original creator of Rust, rule of the not rocket science rule of software engineering. which is to automatically maintain a repository of code that always passes all the tests. And as an aside, I cannot wait for Ferrocene to be qualified for aerospace use, because then we'll be able to say that finally the not rocket science rule will be qualified for literal rocket science. In practice, we use BORSNG as the merge queue, which was our implementation of Boros in Elixir, done by a member of the Rust community, which right now the public instance has been retired, but we continue maintaining our own private instance of it. And what BORSNG does is it takes care of testing and merging one pull request at a time, or at least a group of pull requests at a time. Because even if a pull request passes CI, it doesn't mean that it won't break when you merge it to the main branch. Let's take a very quick example. You have in the main branch a commit that does that drive function, and that passes tests. And then you create two pull requests. One pull request adds a new place that calls the drive function, because it's useful. But then another developer realizes the function is not the current implementation, and in another pull request removes it, and removes all of the places that call it. In isolation, those two pull requests are good, because when you take them with the main branch, they pass all the tests, they compile. But if you try to merge both of them into the main branch, you will result in a broken in a main branch that will fail the tests, because at some point you will have removed the drive function, but you have a place that calls it that you didn't remove in the original pull request, because it wasn't on mine yet. The merge queues solve this by testing one pull request at a time and testing it with the current main branch. So what it means is that you put both pull requests in a queue, and the bot will only first test the first one. And it sees that it passes the tests because adding a new call to the drive function works when the drive function is in main. But then, so the bot merges it into the main branch. But then it tries to build the new one, and it tests the merge commit of the new main branch, the one we just created with the latest merge, and the PR we want to test. And there the bot sees that that it will fail, and it doesn't merge it. Using a merge queue is great when you have a repository with a lot of activity from a lot of developers, because it prevents the main branch from ever being broken. And I personally also find it useful in projects I'm developing alone, because if you have a long-running pull request based on an old copy of the main branch, CI, on at least most of the public CI systems available, only test pull requests with the old main branch they were built on, based on, rather than the latest one. And so it really helps with software quality. And also another thing we take inspiration from the Rust project on is that we run all of the tests and build a full release for every single pull request we merge, regardless of what pull request changes, because we might have a pull request that includes so many new things that, of course, it needs to be fully tested. But there might be a pull request that just fixes a typo in the documentation. With our approach, we still run the full test suite across all of the architectures we support, and we build a full release for all of our targets for that type of fix. This is actually good, even though it's on some senses, it's fairly wasteful, because we are running tests that if you just fix a typo in the documentation is not going to matter, not going to cause tests to fail. But this prevents whole classes of failure when your dependency tracking that checks which tests to run depending on which chains fail, and don't detect that they must have actually run the tests. And so it makes it also improves the main branch from always being green, but also it aids how we do releases, because now we don't have a separate build process for releases that could fail, because releases are built as part of CI, and if building the release fails, it's not going to get merged. And so our release process in the end is basically a glorified copy and paste, because it just takes the release that was built by CI for the latest commit and publishes it. In general, all of the, as I said before, all of the processes are documented. This is just a quick overview of the ones I think are the most important, but I don't want this talk to be Pietro reads the Ferrocene qualification documents aloud. If you want to learn more about our processes, they're all publicly documented. And this is our processes. Now we go to the second to last document, which is the qualification report, which is actually fairly simple. It's just a table of the tests we executed. It's the summary that gives to the assessors the proof that we ran all of the tests we claim to run, that all of them were linked, and that we followed our processes. And I want to also go into a quick aside here on how did we run the tests on the bare metal target, because Rust, of course, supports running in an environment where you have an operative system, like where you have Linux, for example. But it also supports embedded targets, no STD targets, that we call bare metal. For example, Ferrocene supports the ARM V8A bare metal target. But how do you run the tests? Because the Rust test suite actually depends on having the STD crate available. It wants an operating system to run. And honestly, it's just not worth it to try to change, because Rust test suite right now is around 20,000 tests, and reverting all of them to be running in an embedded system is too much work. So we cheated, in a sense, because the advantage we have is that we control the compiler. And so we created a new target that we're not distributing to customers, because it's just an internal thing for testing, that has the same configuration as the bare metal platform, but has the standard library enabled for Linux. Because in Rust, a good design of Rust is that all of the APIs that depend on the operating systems are part of the STD crate. And you don't ship the STD crate in a bare metal target. So we created this weird target that had STD for Linux, but it was on bare metal. And this way, we are able to easily and reliably run the tests for the bare metal targets that we ship. So many tests were broken. Like, I'm pretty sure we are the first people actually doing it, just for the sheer amount of failures we had to fix. And all of the fixes we upstreamed, so we sent pull requests to the Rust project to fix those. And so if you want to try that now, it's more feasible. But yeah, that's how we tested bare metal targets, which was one of the biggest challenges we had to face for Ferrocene. And so we get to the last document, the safety manual. What ties everything together? The document that we give to our customers for how to safely use Ferrocene. And this document is fascinating, because it's something that I want in every single industry, because it's a piece of documentation that customers are legally required to read and understand. Like, imagine writing your software documentation and your customers being legally liable if they don't read it. It's awesome. And because the safety manual describes the constraints customers have to follow, which is what I was mentioning before at the starting the evaluation report. Like, we can say, you have to do something to be able to safely use Ferrocene. We could say now, in our safety manual, you have to manually review all the assembly. We wouldn't sell a copy of Ferrocene because people will go to our competitors. But if there is, for example, a soundness issue in your Rust, because there are a fair amount of soundness bugs present in the standard library, you can just write guidance on how to avoid them. If we cannot write a fix yet, because they might require larger factorings of how the type system works, we can just say to customers, don't write this code pattern, and manually check that you're not writing this code pattern. We can defer checks and defer fixes to our customers. And it's something that we want to keep extremely low, because, again, it's manual work for our customers, and if we have too many of them, customers are going to go to a competitor. But these are key advantages in how we are able to maintain safety. Which brings me to the last thing, which is the known problems. what bugs are we currently know of in Ferrocene. And even here, instead of fixing them, we can provide guidance on how to avoid them. And customers are legally required to follow it if they want the qualification to hold. This one is actually the only part of Ferrocene that is private, mostly for logistical reasons, because if a customer shares a sample code that exercises a bug, they probably don't want us to publish it and open source it on the internet if you're thinking about large automotive customers. But for Ferrocene right now, the known problems are just a curated collection of the upstream soundness issues. So there is nothing secret. There are no secret Rust bugs that only we know of. And that's it. This is all of what it takes to qualify a compiler. Now you just need to take it and build all of the documentation together and send it to an assessor to review. In our case, we use TUVSUD, which you see this logo everywhere, like if you actually start to look for it. And so TUV took our documents, reviewed them. We had a few review cycles where we gave the documents. We had a few review cycles where they gave some feedback, we fixed it, and so on until it was good for them. And they gave us the shiny stamp that we can now use in conference talks, for example. And we were very careful to make sure that qualifying new versions of RC is not going to be hard. All of the processes we've done are there. They're not going to change. We can change them if you want to, but we already have processes that work for us. Rust releases are really small nowadays. You see that there are some releases that have a lot of features, and some releases that, as a member of the Rust release team, as part of my volunteer tasks, I don't even know what to put in the announcement blog post because there's nothing notable in the new release. So it's not hard to update the test suite and the language specification to cover the new releases. And also, we heavily invested in automation. We don't need Rust to slow down to be used in safety critical. If we take an approach that is taken by a lot of the legacy safety critical compiler vendors, yes, maybe, but we tried really hard to make sure that we can bring new energy into the safety critical system, in addition to a new language, that we can make sure that we can deliver a qualified version for the highest level of assurance with fast release cycles. One of the ways we do that is we pull new changes from upstream as fast as possible. We have a daily job that opens a pull request with everything that changes. And usually, we are not far behind upstream. This is way better than basing off an old version and then every few months having to rebase over the new version of Rust, because there might be not that many surface changes to the language, but the Rust compiler gets heavily refactored all of the time. So if you ever maintain a Rust fork, you know how hard it is to keep up and stay up to date. Ferrocene is usually just a day or two behind upstream. We have, in addition to our qualified channels, we have our channels that are automatically published that track Rust nightly, beta, and stable. And usually nightly just a few days behind. Stable is often released the same day or close to the next day. And this is all thanks to the automation and our desire not to slow down Rust and Rust release cycle. This was not just my effort. I was one of the first employees of Ferrosystems working on Ferrocene, but there were a lot of colleagues of me at the company and also external collaborators that we had the pleasure to work with in the past. And so thank them. Don't thank just me for bringing Rust to safety critical. And that's it. Again, this is just for qualification of the compiler. Certifying programs that go into a safety critical system is way harder. And for example, the next thing we're working on at Ferrosystems is certifying libcore, so that you can start using Rust without having to do the certification of core yourself. But I think these processes could be useful for anyone in all other industries. You don't have to actually do the matrix to figure out what the tool impact is, but none of these processes are like bureaucracy for the sake of bureaucracy. They're actually fairly good ways to improve the quality of your software. And so the big takeaway I take from working for the past 3 years on safety critical is that there is a good reason why these processes are in place. Of course, a good reason for safety critical because a lot of the standards are, frankly, written in blood. A lot of what is in the standards was explicitly written there to prevent a crash, a failure that harmed people in the past. But you don't have to, if you work on a mobile application, a web backend, you don't have to follow them to the letter. But a lot of these processes might help you make your software better. And so thank you for listening. And I hope this was insightful and shed a bit of light into the world of safety critical.